Hello, this is Team 18, and we're presenting our major project for IRE for the monsoon semester of 2018. Our task was to solve this problem of uh, being given a conversation with two turns of context, and we have to classify the third user utterance in the conversation as one of four classes: happy, sad, angry, or others. As we can see, there are four classes, but considering how there are a large number of sentiments other than happy, sad, and angry, the distribution of the data set provided to us is also skewed, with only 8% of the samples belonging to one of the three classes and the rest belonging to the others class. At the initial brainstorming and going through previous papers, we realized that the most effective method to solve the problem would be through deep neural networks. This is because we believe that the function that we're trying to model is going to be extremely complex and will be better suited to deep learning methods. Thus, all of our approaches are deep learning. Um, our approach is our approach stands along the following steps. First, we try to represent our text, our dataset in a format suitable for application of statistical methods of AI. Secondly, we use feature engineering to emphasize attributes that we think are important. And here, textual units refers to words, sentences, and whole conversations. Lastly, we experiment with varying values for hyperparameters and various other architectures, including models with CNNs and RNNs. Our first model, which is also a baseline model, is very simple. It's an LSTM which takes glove vectors and puts it through a dense layer utilizing a sigmoid activation function. This gives us class-wise probabilities for the four classes: happy, angry, sad, and others. We use LSTMs because LSTMs help retain contextual data. This model gives us around 56% uh, score, and as I said before, this is our baseline. The second model we tried to employ a CNN because we believe that CNN could properly summarize the data. Same with the max pool at the end of the CNN. So in model 2, the model goes like CNN with 6 filters, a max pool, then an LSTM followed by a dense layer, and finally a 4-class sigmoid activation layer. Unfortunately, our scores actually get worse. Some of the reasons we think this is due to is that the CNN actually just messes up the conversation. It jumbles it up and ends up losing information instead of making more sense of it. And the same stands true for max pooling as well. Thus, we've not really tried working with CNNs after this. We instead try to go for feature engineering. The features we have tried are listed here: hedges, factive verbs, assertive verbs, implicative verbs, report verbs, entailments, subjective verbs, and whether the subjectivity is weak or strong. Lastly, we also take into account polarity, since positivity and negativity in our words will also indicate what the sentiment is. Um, as you can see, these features are partly influenced from research into linguistic bias. The idea is that the features reflect subjectivity, and since sentiment is a highly subjective phenomenon, these features should help bring emphasis to it. What we do is that we create a feature vector and we append this to our regular glove embeddings to produce what we call feature augmented semantic word embeddings, or FSWE for short. In the rest of our models, we will be using FSWE everywhere, as is quite clear after we look at model 3. When we replaced glove vectors with our own FSWE in model 1, we found an increase in the score by 3%. Further changing glove embeddings from 100 dimensions to 300 dimensions raises it by a further 1%. So as I've noted on the slide, we're going to be using FSWE everywhere now onwards, since it does seem to have an overall positive effect. Our next model, model 4, is our current best model. Um, while we have only listed 4 models in our slides, These are not the only four that we have tried. We have tried many other approaches listed in the report. However, this is our best performing model and we wanted to present it. Um, Here we have two parallel LSTMs at the beginning, which each of which takes an SSWE representation and a glove representation, respectively. Once the LSTMs process this, they concatenate the vectors and pass them through another LSTM. Uh, we tried experimenting and replacing the LSTM with other kind of layers like dense layers and even bidirectional LSTMs, but all of them resulted in lowered scores. Again, we believe this is due to the fact that LSTMs hold context better than other forms of recurrent, than other forms of neural network layers. As we can see, LSTMs 1 and 2 represent the conversation. The final LSTM represents the correlations drawn from both the semantic and sentiment spaces. The dense layer again extrapolates the vectors into probability distribution, so we can classify them into the four classes we need. In conclusion, performances of all models seem to be directly correlated to the following: the amount of information, the amount of importance given to context, semi-supervisation via external feature generation, and lastly, hyperparameter adjustments. Um, at the moment, we also have other ideas which seem worthy of trial, and we have not been able to do so in the given span of time. However, we do plan to continue participating in this contest, which will be ongoing till around the month of February 2019, and we hope we end up getting better performance. Thank you. These are our links to our GitHub repository and web pages and our references. Thank you.